It is 2, so we will get started for today. And our topic for today is all about fatty acids. So we're going to be moving on to our last major biomolecule here. So we've already covered the amino acids, we've covered nucleotides, we've covered sugars. Now our last category here at the end of the semester are fatty acids. So we're just going to go over the basic fatty acid structure and naming scheme here to begin with. So what is a fatty acid? Fatty acid has a carboxylic acid, shown here, and then a long hydrocarbon tail. And the tail can really vary. The most common types of fatty acids you're going to see are 16 and 18 carbons. Less than 14, greater than 20, possible, but unlikely. Okay, I just might have broke up there. So carbons less than 14 or greater than 20, they are possible but unlikely. And here I'm just showing some common types of fatty acids, and you don't need to worry about the names like stearic, oleic, linoleic. What we're going to learn about is how to number fatty acids and name them using a numbering system. So I have the names, or rather the numbers of these fatty acids listed here. So let's go over how we name them. So what you do is that you always start with carbon number 1 on the carbonyl carbon, and then you just start counting how many carbons you have. That's what this first number means. This 18 means in total in my fatty acid, I add 18 carbons, colon, then the number of double bonds. So this is total number of carbons, total number of double bonds here. So this is an 18 colon 0. This is what we call a saturated fatty acid. Saturated means you have the maximum amount of hydrogens that you can have. While all of these other 3 fatty acids are unsaturated because they have at least 1 double bond. And what you do when you have a double bond is that you start counting like normal. So carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. So here's carbon 9. That's where our double bond starts. So this is called 18 colon 1, the 1 because we have 1 double bond, delta 9. This delta 9 says our double bond starts on carbon 9. All right. So linoleic acid is 18 colon 2 because we have 2 double bonds, and they're called delta 912 because the double bond starts at carbon 9 and carbon 12. Here, linoleic acid, 18 delta 3 for 3 double bonds, delta 912 15 for their starting positions. Now, if we look at alpha linoleic acid, this is actually an omega-3 acid. So there is another way to count your carbon numbers in fatty acids. And you start with the last carbon. You call that omega-1. And so this would be omega-2. And this is omega-3. So if a double bond happens at the omega-3 position, this is called an omega-3 fatty acid, which you might have heard about, just from advertisements. They always like to point out omega-3 fatty acids are in their products because it does have health benefits. Now, when we look at the type of fatty acids in animals and plants, most of them are unsaturated. They have double bonds, and a lot of them are polyunsaturated. So if all these are unsaturated, these 2 are polyunsaturated because they have more than 1 double bond. And when you're polysaturated, as we see in the numbering scheme here, your double bonds are going to be separated by 3 carbons. So 912 and 91215. And usually these are in the cis conformation, not the trans conformation for steric reasons. And like we're going to look at, when you have these unsaturated fatty acids, it's much harder to pack them together. What I mean by that is if I was just looking at a saturated fatty acid, the tails of the saturated fatty acid could line up like this. They would like line up almost perfectly, which means that they will stick together and more likely to form a solid. But if you have a double bond like that, it's harder to pack these together because of that double bond. And so these will have a much lower melting point. So that's what I mean by can't pack as well. It's how close their tails can come together. So that is our naming scheme on fatty acids there. So let's do a little bit of practice. I have 4 different fatty acids. Just take a couple minutes here. See if you can figure out the naming schemes of this fatty acid. Tell me if it's saturated or unsaturated, and if it's omega-3 fatty acid. So I'm going to give you about 2 minutes, 2 to 3 minutes to do this, and I'll be back with the answer. If you have any questions, please let me know. All right, so let's take a look at these fatty acids, how we name these. So again, start from our carboxylic acid carbon, name that 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this fatty acid has 18 carbons, 1 double bond. So this is 18:1. And the double bond is at the 9th position, delta 9. It is unsaturated because we have a double bond, and it's not omega-3 fatty acid because we don't have a double bond there. B, again, do the counting. 1, 2, 3, 4. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is a 20 fatty acid. And we have 1, 2, 3, 4, 5. So this is 20 colon 5. And we have to say where all the double bonds are. So delta 5, 8, 11, 14, 17. This is again unsaturated because we have double bonds. And it is an omega-3. Because remember, omega starts at the very last carbon. So that's omega-1. That's omega-2. That's an omega-3. So go on to fatty acid 3, carboxylic acid's right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this is an 18 carbon as 18 carbon fatty acid. 1, 2, 3. We have three double bonds rather. So delta 9, 12, and 15. This is also an omega-3, omega-1, omega-2, omega-3. And it's also unsaturated because we have double bonds. Lastly, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. So our last fatty acid here is 18 carbons, 2 double bonds, 18, 2, delta 9, 12. This is unsaturated, not an omega-3, but it is what we call an omega-6. So omega-1, omega-2, omega-3, omega-4, omega-5, omega-6. So this would be called an omega-6 fatty acid instead of omega-3 fatty acid. So that is how we can name our fatty acids. Any questions about that? Would A be? So technically A, you could call an omega-9, but usually people just say omega-3 and omega-6 for classes because those show benefits inside the body. So yes, it is an omega-9, but they're not classified that way. Usually people classify omega-3 or omega-6. All right. So one of the things that you should really train yourself as a science student is learning how to read charts and get information from those charts, get trends from this chart. So what I want you to do is just look at this chart and tell me, or you can write down and I'll tell you in a couple minutes, what are all the trends in data you see presented in this chart? Try to get as many data trends as you can. So I'll give you a few minutes to look at this table and look at some data trends. This is very good practice because a lot of scientific data is presented in tables like this. So it's very important to know how to do this. All right, so let's look at some of these trends in data. And there's a lot that you can pick out. Let's start by looking at the very top of the table. And here we can see that in our saturated fatty acids, as we increase tail length, melting point also goes up. So there's correlation between tail carbon length and melting point. As that increases, melting point increases. And the reason for this is packing. Tails, when they're longer, they have more interactions between them. Because since these are saturated, they pack well together to begin with. And when they're longer, you have just more interactions. So that's one trend. Another trend that you could have saw is that they always increase in units of 2. So generally speaking, fatty acids add 2 carbons at a time when they're being created. So usually they're even numbers. Not always, though. There are odd number of fatty acids out there. It's just in general, they're even numbers. If you take Biochem 2, we'll talk about why that is. It's how they're created. So that's another trend you could have saw. Something else. When you add a double bond, so if we're going from 16-0 to a 16-1, or an 18-0 to an 18-1, adding that double bond decreases melting point a lot. So as you increase double bonds, melting temperature goes down. And we can even see that if we're looking at an 18-1 versus an 18-2 versus an 18-3. The more double bonds you go, the lower and lower the melting point goes, which just means it's easier to turn it into a liquid. Again, this has to do with packing. If you have a double bond, you can't pack very well with your tails, and you're not having those good, strong steric interactions. So that's another trend. And last trend that we already talked about is if you look at the double bonds, they're always separated by units of 3. So double bonds in fatty acids are always 3 apart if you have multiple double bonds. So those are the general trends that I saw in this data table. So yeah, any questions about that? All right, let's move on then. So we can just skip question 3. Question 3 often confuses people, and I don't think it's a good question anyways, now that I was rereading it today. So skip. Don't worry about question 3. It's trying to say, you know, how do tails length and melting point change? I think question 2 gets at that way better. So feel free to skip this question when you go back and review for the test. All right. So we've talked about single fatty acids. Let's talk about triacylglycerols, or TAGs now. And usually in animals, we don't have free fatty acids just everywhere in our cell. They do appear in our bloodstream. They do appear in our membranes. But if we're storing fats, we store them as triacylglycerols. These are very nonpolar, and so they're water insoluble. Remember, we talked about this at the beginning of biochemistry. The thing that makes something soluble in water is its ability to form hydrogen bonds with water. This fatty acid, triacylglycerol, just long carbon tails, that's not going to be easily formed into hydrogen bonds, so it's water insoluble. it's called a triacylglycerol because it has the backbone of glycerol showed here. And these are our acyl groups. So we have 3 acyl on a glycerol, triacylglycerol. They're going to be your main energy reserve. We did talk about another one last week. Glycogen is another energy reserve in humans. But the amount of glycogen, which is just glucose, the amount of glycogen you have in your body would last you maybe like a day's worth of energy. For fat, if you have 30 pounds of fat on you, you can last 3 months, just speaking in terms of energy. You would still need vitamins and minerals, but if you're just talking straight energy needs, fat is the main go-to for animals. And it's because they are hydrophobic. For glycogen, the sugar energy storage, glycogen is surrounded by water. And so we have to carry that water around us when we are storing glycogen. Fat, we don't. We can store a lot more energy with a lot less weight because of fat. And inside our adipocytes, which are shown here, our fat cells, you usually have a mixture of different tags. If you're looking at plants versus animals, plants usually have a lot more unsaturated fatty acids than saturated. And you know this if you cook a lot, right? Your olive oil, which is from plants, is going to be a liquid at room temperature. While something like lard, which is from animals, it's more likely to be a solid. The reason why olive oil is a liquid is because it has more unsaturated fatty acids than lard does, which has a lot more saturated fatty acids. And when you just look at the health aspect of it, unsaturated fatty acids are generally better for humans to eat than saturated fatty acids. So that's our triacylglycerols there. There are energy storage in these adipocytes. So here's a good thought-provoking question. So tags, like I said, we just use for storage. However, another place you can find fatty acids, it's a lipid bilayer. Why would you not find tags generally in the lipid bilayer? What is different from a fatty acid in the lipid bilayer versus a fatty acid in a triacylglycerol? So give people a minute to think about that. If you have an idea, please feel free to share it. But yeah, think about that. What's different between fatty acids and plasma membranes and fatty acids and triacylglycerols? Because nonpolar. The opposite. In that the lipids in the plasma membrane are nonpolar as well. But they are something that has to do with it that tags are not. Because they're not used for energy. That is true. That is true. The lipids in the plasma membrane are not used for energy and tags are. But why wouldn't you find a tag just randomly in the plasma membrane? Why couldn't they accidentally go there? What are tags missing that lipids in the plasma membrane have, just speaking biochemically? Receptors, the lipids themselves don't have receptors. Receptors are generally big protein complexes, so it's not that. What I was getting at was that in the plasma membrane, you have a very polar head group, and then the tails are nonpolar. And so that's what the membrane is. Glycerol although it has oxygens, this is not really a polar head group, right? So the big difference between a tag and a lipid in the plasma membrane is the head group, which we're going to look at today as well. But these have a lot of oxygen, some charge groups, and all of that. So that's the main difference between a fatty acid that's in a tag and a fatty acid that's in the plasma membrane is what's on the head group. So this is polar or charged. And glycerol by itself, glycerol could be somewhat nonpolar, but in the triacylglycerol form, it is not polar at all, just because of all those fatty acid tails. So let's look at some of the different head groups that can make up the plasma membrane. And so we're going to look at our glycerol phospholipids to begin with. First, let's break down the name, right? Glycerol, what we just looked at, but if it's a phospholipid, all that means is that instead of an OH here, we have this phosphate group. And depending on what's connected to that phosphate group, we give it different names. So if you look at the glycerol phospholipid down here, these R groups mean fatty acids. These R groups are going to be our long carbon tails. This X group is going to be one of these elements. And based on what it is, it gets a different name, and it also has a slightly different function. So if X, for example, if that X is a hydrogen, that's phosphatidic acid. If it has an ethylamine, it's phosphatidylethanolamine. Choline, phosphatidylcholine, serine, phosphatidylserine, so on and so forth. So it's usually phosphatidyl than what's on it. So for these, it's going to be really helpful for us if we can learn to recognize the head groups and their names, because based on what the head group is, they have a different function in the plasma membrane. So yeah, make sure that if you see like phosphatidyl, if you see this inositol on our phospholipid, know that that's called phosphatidylinositol. If you see a choline, which is this, it's called phosphatidylcholine. And that's kind of my hint for you for saying that I'm going to show you a glycerol phospholipid on the next test and give it one of these head groups. And it'll probably just be multiple choice and say, you know, what's the name of this glycerol phospholipid. So just make sure you review these structures. So here it's a way for you to like force you to study for this. Just look at these groups and ask which ones can hydrogen bond. So I'm just going to go over this really quick. So the idea is instead of this X, we're going to put one of these groups and ask, can that group hydrogen bond? Well, instead of an X, if I had a hydrogen there, yes, that can hydrogen bond. If I had an Na3 plus there, yes, that can hydrogen bond. Choline can't because it has CH3 group. So remember, if you just have carbon and hydrogens here, you can't really form a hydrogen bond. Serine can, inositol can, glycerol can, and I know this is cut off a little bit, but phosphatidylglycerol can. And what phosphatidylglycerol, this is the weirdest looking head group. It has like another glycerol connected to much more phosphate. So it's almost like two lipids combined to make phosphatidylglycerol, because this X would just start with a chain of carbons and hydrogens, and lead to another glycerol molecule, another phosphatidylglycerol molecule. So that's definitely the most interesting head group you can have there. And then B, autoimmune diseases recognize DNA, can also recognize phospholipids. Therefore, what must they be binding to? So this is kind of a throwback to our discussion on antibodies. And the way antibodies work is that they find an antigen. Well, if an antibody can bind both the DNA and phospholipids, their antigen must be phosphate then, because that is the common molecular motif between a glycerophospholipid and DNA/RNA. All right, so I just want to take this moment, ask, so far, any questions, any confusions, or anything at all about what we've covered today? All right, if not, we can go on. So let's look at some other classes of lipids that we could find in our plasma membrane. So glycerophospholipids are a big class. Another class is the sphingolipids. And what a sphingolipid is, it's a lipid, if my internet goes bad again, it's a lipid that has the head group of a sphingosine, right? So this often confuses people, but this head group is called a sphingosine. If you connect a fatty acid to this nitrogen, that becomes a sphingolipid now. It's the same type of naming scheme we use for triacylglycerols or a phospholipid, a glycerol phospholipid. The glycerol phospho means the head group, then it's saying you have a lipid attached. Sphingosine is our head group, and then you have a sphingolipid. What is interesting about our sphingosines is that you already have a lipid that's kind of like built in. You have this 1, 2, 12, 14, 15 carbons, hydrocarbon compound with this very early double bond. And out of all the lipids, your sphingolipids are going to be what makes up the highest percentage of lipids in your membranes. So they have a very important role in your membranes. So most of your lipids are these sphingosines. And you have different types of sphingolipids, and in general, that when you just put any lipid onto this nitrogen, the class is called a ceramide. And that's how we get our different sphingolipids from there. So it's really weird terminology. Where a sphingosine, you add the lipid, you call that a ceramide, but these ceramides make these different sphingolipids, right? Very confusing naming there, and always trips people up. So just remember, sphingosine's the head group, ceramide, we add a lipid to it, or they're also called sphingolipids. So ceramide is kind of like the more general name there. And we can make it even more confusing because, of course, we can. When we take these sphingolipids, we can attach different head groups to the backbone that does not have nitrogen on it. So remember, for our sphingosine, this carbon is always a fixture. On the nitrogen, we can put a fatty acid there. That's a sphingolipid. Then on the last carbon, we can put different head groups. So let's look at the different types of sphingolipids that you can make. The first is and the word's cut off there, is a sphingomyelin. And what a sphingomyelin is what is another name is a sphingophospholipid, right? Phospholipid. Backbone is the black part here is our sphingosine. So again, very confusing wording, very confusing naming that's used for these, but you can start to break it down and it'll make sense once you have the parts. So sphingomyelins or sphingolipids or sphingophospholipid, these are going to be your most common sphingolipids. So they are the most common type of lipid that makes up the majority of your plasma membrane. So they're very common, these sphingomyelins. You can have different types of sphingomyelins that have different head groups right here as well. So you can have phosphorylcholine, which is being shown. You can also have phosphoethylamine. So that's what's attached to the phosphate can actually change as well. And like I said, they're common. So 10 to 20% of your plasma membrane is made out of these molecules. If instead of this phosphate group, you have sugars, you call that a cerebroside or a glycosphingolipid. Again, let's break down this word. Glyco, when you see that, you should think sugar. Sphingo is the backbone, that black part. Lipid, fatty acid. So it's just a head group with a sugar. Here you have different types. So if your head group's galactose, you get a cerebroside or a gluco, right? So really, these names are horrible. All this is saying is that here on this head group, you can have a galactose or you can have a glucose. That's all that means. And they're non-ionic, which means that all of the OHs coming off your sugars, they're going to be OHs. You're not going to have any negative oxygens or anything. You're not going to lose your hydrogens. And a more complex head group is called the ganglioside. Here, instead of one sugar, you have 5 sugars. And this group is called the salicylic acid. These make up a lot of the lipids in your brain. So 6% of all the lipids inside your brain are made of these gangliosides, which is this a sphingolipid, again, this black, the fatty acid, the green, and this very complex head group. Don't worry about knowing every single sugar in this head group. If you just know it's many sugars together, that's okay with me. And if you just know that this is called a ganglioside, that's okay with me. So I know that's usually people have found this stuff like very confusing the first time they hear it because it's a lot of difficult words and it's probably the first time you're hearing a lot of these words or looking at the words with the pictures. So this is really something that you just have to look at it a couple of times, refresh or review, match up the picture to the word and try to just remember the function of these lipids. And that's usually the best way to get this down, just repetition. But just to begin with, are there any questions about this information? Like I said, I know this is something that probably just you need a little bit of time to digest normally. as my dogs go wild here. All right, so I'm going to do my best to talk over the barking dogs here. Hopefully they calm down in a second. All right, so question 6 here is just to test your understanding. Which of these is true of sphingolipids? So this is a very, very like a question that you would see on the test. So try to match this information up with what we just talked about on the previous slides. And I'll give people like 30 seconds, a minute, think about this, and then I'll be back with the answer. Right, so let's think about what are our sphingolipids again. So let's see these statements and just say if they're true or false. So 1, contains a glycerol core with a sphingolcholine head group. That is not true. They don't have glycerol. They have a sphingosine core. And it's not necessarily they have a phosphocholene. They could, that's possible for them to have phosphocholene, but they definitely don't have a glycerol core. So that's false about sphingolipids. 2, they have a modified sphingosine. That's true, right? That is the backbone, the head group mainly of the sphingolipid. They have a sphingosine that has a fatty acid attached to it and some other head group usually attached to it as well. So yes, they have a modified sphingosine. That's the head group. Often functions as receptor components of membrane. So we didn't talk about that, but they are in the membranes. And yes, they are usually some kind of receptor component. Usually things bind onto these lipids. So that's true there. Function as a precursor. Sphingolipids are the last step in the process. The sphingosine, that's a precursor to make sphingolipids. But once you have the sphingolipid, that's like the last thing you're trying to make. So they're not really a precursor for anything. So that's going to be false there. So here, the best answer you could pick is D. And that sphingolipids, they have that modified sphingosine. They're usually found in the membrane as some kind of cellular receptor. All right. So any questions about anything that we have gone over so far today? All right, if not, it's almost 2:50. So instead of jumping into another topic and going long, I'll just cut it off here. So we just have a couple more questions, which is a good place to start on Friday as a good review for what we went over today. So yeah, I will put up homework as always to just give you some more practice on the concept we talked about today. If you have any questions about anything, please always let me know. Email me. I'll be happy to help. Otherwise, thanks for stopping by or watching on YouTube. Always appreciate it. And hopefully I'll see you on Friday. Take care, people.